just starting to discuss decoherence, and let me just remind you of a few things. So we have some system plus some large environment, which we usually call a bath, and there is some interaction between them. In the end, we will be interested in what happens with the system, and typically we will look at some interference effect, and we will see how this interference effect is then destroyed by the interaction with the environment. And so the first example that I gave, so this camera is not really set up. Okay. So the first example I gave was the simplest possible example you can have for the system, which is just to have a spin. And for example, if the Hamiltonian of the spin would just describe some energy h per omega to the up state, then in the absence of coupling to the bath, this is just a spin in a magnetic field, and so if you prepare it in a superposition of up and down, which means that it points into the x direction, it will just precess in the xy plane. And so if you then plot a sigma x as a function of time, you would see these nice cosine type oscillations. Now the question is, what happens if you couple it to a bath? Everything will depend on how exactly does the interaction look like and how exactly does the dynamics of the bath look like. The simplest kind of interaction is this Q and D type of interaction, which we already discussed for the measurements, where the interaction itself would commute with this Hamiltonian. So if you want to see an explicit interaction Hamiltonian, this Q and D type of interaction would look like this for this two-level system. So the up state would couple to one particular operator of the bath, let's call it the up, and the down state would couple to another operator of the bath, let's call it the down. So that would be an example of a Q and D interaction. And so what happens then is that depending on whether I'm in the up or in the down state with respect to the spin, the bath will evolve differently because it is subject not only to its usual bath Hamiltonian, but also to this additional V up or V down. And so two different bath states develop. This is exactly the situation we already discussed for the measurement. You will have two states, Chi up and Chi down. So the state after some time of system plus bath would look like this. If I suppose I have an equal superposition initially, but this doesn't really matter so much, I would have down times Chi down of T. This is the state of the bath, given that my spin is in the state down, plus there is up times Chi up of T. And then there is the bare evolution, which in this case is simply oscillation at the frequency omega. Now, if you go ahead and now calculate, for example, the expectation value of sigma x, you will find that the expectation value is modified. It's modified precisely by the overlap of these two bath states. So that is what we wrote down. So in particular, in the simple situation where this overlap is purely real valued, which need not always be the case, but simpler in that case to see what happens, the overlap just becomes a prefactor in front of our cosine type oscillations. So that would be Chi down of T and Chi up of T. Or more generally, even if I were to say calculate sigma y, again the same overlap would appear. And so you can express that by calculating the reduced density matrix of our system, that is our spin in this case. And let's write down, say, the element up, down, which is one of the two off-diagonal elements. and then it happens to be precisely this overlap in the opposite order. So there's chi up of t to the right and chi down of t to the left, if you work it out, times the bare time evolution, the evolution of the off-diagonal element in the absence of the graph. So let's call this 0, the bare time evolution, which would just be an oscillation at this frequency. Okay, now if I plot this, if I plot the expectation value of sigma x, for example, the typical situation will be that as time progresses, the two graph states diverge more and more from each other, so the overlap gets reduced more and more. And so typically I have just some decay, and the envelope here is determined by precisely the time evolution of the overlap. This need not necessarily go down to 0. That depends on all the detailed properties of the graph. It could also show revivals at some point in time. So there are many different possibilities depending on the physical situation. But that is, so to speak, the standard situation. Okay. Now, this is the quantum description. What I want to discuss now is that you would be able to have exactly the same behavior also if you just couple to classical noise. If the frequency, the transition frequency between spin up and spin down, the omega, is just time dependent. So then your initial Hamiltonian, the Hamiltonian of the spin itself, is the full Hamiltonian in this case, because you don't talk about an environment anymore. You just say, I have provided externally some fluctuating potential, and that would then be, say, the projector onto the upstate times h bar omega. This is still a fixed deterministic frequency, plus some v of t. And v of t is the noise. And so if I plot this, then really you should have in mind some random process. And again, of course, all the details of what we are going to discuss will depend on the details of the stochastic properties of this random process. Now it's even simpler than before to calculate the time evolution of the wave function. It's purely a wave function of the spin. Basically, it's just this free precession. The only difference is that the omega effectively now becomes time dependent. So in addition to the omega times t deterministic phase, there is an additional random phase. So I would have psi s of t equals 1 over square root of 2 down plus up times e to the minus I omega t minus I phi. Now phi is really a function of time. And if you work it out, you immediately see this should be nothing but the time integral over the fluctuating energy, over the fluctuating v of t. So this is 1 over h bar integral v of t prime. And so the fluctuating potential leads to a fluctuating phase, and the important conceptual point is that in each run of the experiment, this phase will be different. That's why it's called noise. And so in each of, since we are dealing with a single quantum system, in each run of the experiment, you can only measure once before you scramble the state, before you at least make the state collapse to up or down, for example. And so, because of that, you will have to do many experimental runs to measure curves like the ones shown here. And in these many experimental runs, each time the phase will be different. So what you will have to do is to calculate the expectation value of sigma x with respect to the state. You will get some result that depends on the phase, and then you still have to average over the phase. So what is the expectation value of sigma x? That is just like before, only now we don't just have cosine omega t, but in addition there is this extra phase phi t. That looks still like some deterministic time evolution, but as I said, you have to average over the phase. And now again, the details will depend on the statistical properties of the phase, which are dictated by the statistical properties of the noise. But you can see qualitatively very easily what happens. If I were to draw the expectation value as given here for any particular trajectory of phi of t, then it could look something like this. It would be oscillations whose effective frequency changes in time because I have this phi of t, which is irregular. And so sometimes it's faster and sometimes it's slower. But this is only for one particular trajectory of phi of t, so to speak, in one run of the experiment. But as I said, you can't really measure this continuous curve in one run. You can only measure the state of the spin at one spot. So in the next run of the experiment, you would have a curve that looks somewhat different. And then again, another curve that looks even more different, and so on. And what you see very easily is you always start at the same point. That's our initial condition. It's always the same. But then you accumulate the phase, and it becomes more and more important that the effective frequency fluctuates, and after very few oscillation cycles, these different trajectories completely run out of phase. And so if you average over them, you quickly average down to zero. And so this is what is called dephasing, because really the phases differ from each other. So this would be the individual realizations, but if I do the average of sigma x of t averaged over the phase, that is averaged over different experimental runs, then as I said, you just get this decaying envelope. And again, okay, so this looks very similar to the quantum case. And again, everything will depend on the properties of phi. You could also again engineer revivals. It does not need to go down all the way to zero. That depends on the statistics. And we're going to discuss the statistics a little bit later. So here, the idea is just to explain it qualitatively. Okay, so this is dephasing. I will not really make a big distinction between dephasing and decoherence, although I prefer to speak of dephasing in those situations where the interaction is of this QND type, so that only the energy difference between two states fluctuates, and so you get a fluctuating phase. There's also another way of losing coherence, which we will discuss later, when you simply have relaxation, say an atom spontaneously emits a photon, that would also destroy the superposition of the excited state and the ground state of the atom. Yeah? And in that case, you cannot so easily express it in this way. Okay. Now, this was for a spin, and it's an important example of decoherence, because think of all the qubits, for example. But another very important example of decoherence is whenever you have an interferometer, like a double-slit experiment, and there is some fluctuating potential. picture you should have in mind looks like this. Imagine you have two wave packets. They describe one and the same particle, so we're dealing with a purely one particle problem, but the wave packet, the initial wave packet has been split into two, for example by going through a beam splitter, and one part has been transmitted, the other has been reflected, so I have two wave packets. I imagine they are moving into different directions. So if I were to plot also the wave fronts, say the lines of constant real part of the wave function, these would look like that. And then I imagine that the potential is such that these trajectories of the wave packets are curved. And so automatically at some later point they will overlap. I won't even draw the wave fronts here, or maybe I just indicate them. They look like this, okay? Because the lower wave packet is moving upwards and the upper one is moving downwards. Now, if you work out the intensity, that is psi squared, the probability density, then here it would have been very homogeneous, just falling off like the envelope of this wave packet. But in this overlap region, you will find an interference pattern. You will find stripes, and they, in this case, they just look like this. You can work that out for yourself. It just depends on the difference of wave vectors. So the wave vector of the psi squared pattern is the difference of k1 and k2. And so I can also plot, say, if I take a cut through the situation and plot psi squared along this line, I will then just find something like this. Okay. And so for the discussion in the following, I will call this one the left wave packet, and that one the right. So the question we want to ask now is, what happens if there is some fluctuating force? Or more precisely, some fluctuating potential. For example, this might be an electron moving in a semiconductor, and it will feel the distortion of the crystal lattice as some thermal phonons, thermal sound waves travel through the crystal lattice. That would be 190 then. Or it might even travel in free space, and we could have some electric fields from nearby matter fluctuating. So there is some fluctuating potential. Now, since this fluctuating potential corresponds to a fluctuating force, of course, in principle, if it's strong enough, anything can happen. The wave packets can get distorted, their trajectory will change, and so on. But we want to focus on the simplest effect, the first effect that happens. And the first effect that really happens is that you accumulate a phase difference, a relative phase between the two wave packets. And the reason that this is the first effect is actually that if you think about it, if these two wave packets have a large distance and you prescribe some force F, then the energy difference, the potential energy difference is F times the distance. And this potential energy difference, just like before, will determine the fluctuating phase difference. And so you can make that larger and larger, even as the force fluctuations stay constant, even as the effect on the shape of the wave packet or the trajectory remains constant, you can simply make the effect larger and larger by having a larger distance. So you can imagine situations where the first effect is really this D-phase. Okay. So how do we describe this? Well, this is simple enough. We have the total wave function being composed of two parts, the left and the right wave packet. I assume everything is normalized such that the total one is normalized. And then I want to calculate psi squared, in particular in this interference region. And so I take psi squared. And well, that would give psi L squared plus psi r squared plus extra terms. And the extra terms are just psi l star, psi r plus the complex conjugate of this, so psi r star, psi l. And everything, of course, depends on the position. This would just be the sum of the classical probability distributions. That is what you would expect classically. And that is obviously the interference term. For example, if I insert a phase factor here in front of one of the wave packets, the classical part will not change, but the interference term will change. And what it would mean for this interference pattern is that it shifts up and down. If I introduce a phase difference, the interference pattern shifts up and down. So now let's see what happens if I couple to some environment. And for this example, it's easier to start imagining I have a classical noise, simply a classical external fluctuating potential prescribed in my Schrödinger evolution. And then I will average over this fluctuating potential just as I did before with the spin. So if I have some noise that is some v of r comma t, which looks different every time I do the experiment, then the easiest approximation I can do, the simplest approximation, is the one I already told you, that I neglect all the distortions of the wave packets, I neglect the effects on the trajectories, but I keep the effect on the phase. And so that would mean, for example, the left wave packet goes over into the left wave packet multiplied with a phase factor, e to the minus I phi l. So this would be the phase that my left wave packet accumulates. I don't even make it position dependent, in the sense that I will write down an expression that only depends on the motion of the center of mass of the wave packet. Again, this is an approximation, but this is consistent with what I said before. I only want to keep the lowest order effects. So how does this phi l of t look like? Well, the simplest approximation you can make is to say, I just imagine that the spatial scale over which my potential changes is much larger than the extent of any given wave packet. I mean, it's smaller than the distance in order to make it interesting, but it's larger than the extent of the wave packet. And so I then can just evaluate the potential at the center of mass of each wave packet. And then the formula looks just as before. I will just integrate over time the potential evaluated at the instantaneous center of mass. So that would be 1 over h bar integral over time v of. Now, the potential here depends on position, but I will insert the center of mass position. So that would be RL of t prime, for example, if I'm looking at the left wave packet. So that's the left center of mass trajectory. And then you will see what this means. In the interference term, I will get a phase vector that depends on the difference of these two phases. So in the end, for example, psi l star, psi r should be replaced by psi l star, psi r times this phase vector e to the I phi l minus phi r. And then, just as before, I will have to average over the noise. And again, the average over this phase factor will give a complex number of magnitude less than 1, so it suppresses the interference term. So that's the whole idea. What does it mean physically? Well, physically, I already told you that whenever I introduce an extra phase shift, the interference pattern moves up or down. And now I'm just averaging over many interference patterns, each of them displaced by some random amount up or down. And as you can imagine, this just smears out the interference fringes. initial pattern, which, for example, goes down nicely to 0, showing perfect destructive interference, which it can do if the wave packets have equal weight. Then after smearing, I might get something like this. So there is weight at where we had destructive interference, and the peaks are reduced. Okay. And of course, once again, the details would now depend on the statistical properties of the phases, which depend on the statistical properties of the fluctuating potential. For example, what's the correlation time, what's the correlation length, and so on. Now, if you want to look at the same story in a fully quantum mechanical way, again, on the same level of approximation, you can say, how does the state of the environment evolve, given that my particle travels along the upper trajectory? Or how does it evolve, given that my particle travels along the lower trajectory? So that's like asking, how does the state evolve if my spin is up or down? And so that will result in two different states. That's called chi L and chi R. And as you can guess by now, it's the overlap that replaces this average over the phase. So again, in words, this is the overlap between the two bath states that result from the particle traveling either along the trajectory L or R. And so now we can go back to this, to what we learned about measurement. Of course, our environment will just be, say, a crystal lattice into which the electron moving along this direction emits some phonons and thereby reveals its presence. So it's not really a detector. We will never read this out. But from the point of view of the electron, that doesn't matter. It still feels the decoherence. And so people say that this is a sort of which way information that is revealed by the interaction between the electron and its environment, and that leads to decoherence. So it is as if we were doing a measurement. And so this is a very important concept that even if you don't make use of the information, it's already enough to lead to decoherence. So that is always the question you should ask. Is there, in principle at least, a way, would there be a way I could tell afterwards that the particle has traveled this way or the other way? If there is, in principle, a way of telling, then there will be decoherence. Now this all seems relatively simple. Of course, it would remain to calculate these states of the environment. But I now want to have a word of caution here, because there are situations when it seems as if there is a lot of reduction of overlap here, so it seems that like there is a lot of decoherence, but you will still see a perfect interference pattern on the screen. And so these situations always have to do with the following physical story. Imagine your electron, for example, interacts with the crystal lattice, which just means it distorts the crystal lattice around it. So that would be the distorted crystal lattice, and people call this a polaron. Now as the electron moves, this distortion moves together with the electron. And so, to speak, the electron together with the distortion form a new quasi-particle, which, for example, will change the effective mass of the electron. Now, in our kind of language, we would say, what happens here is that the full state of my system, that is electron plus crystal lattice, can be expressed like this. I integrate over all possible positions at which the electron could be. I have an amplitude psi of x that the electron is there, or rather that the polaron is there. And then I have just the basis state expressing the fact that the electron is at this position x, but I multiply it with some state of the environment that also depends on the position of x that would represent the distortion of the crystal lattice given that there is an electron at this position. So that is the polaron in a crystal lattice, but the same situation also happens even if the electron is in free space, because even if the electron is in free space, you know that if you take into account that it is charged and that it therefore interacts with the electromagnetic field, there will of course be field lines. Which get progressively weaker as you go out, of course. And that means, from this point of view, the state of the electromagnetic field has been changed. It is distorted in the vicinity of the electron, just like our crystal lattice. And this distortion moves along with the electron. So, again, in principle, it should be described by such a wave function. And so, if you take this serious, you would say, for example, if my electron is at two different positions corresponding to the wave packets, the left and the right wave packet, then I also have chi L and chi R, two different states, and their overlap can be very small, depending on the details, but there will be a reduced overlap. So, now you could go ahead and do the following. You could calculate the reduced density matrix of my electron only. And since the reduced density matrix depends on two indices, x and x prime, I also have to plot it in 2 dimensions. And let's compare two different situations. One is the situation without coupling to such an environment, just the free electron, the free particle, which is not even charged, so as not to couple to the electromagnetic field. And so if that is brought into a superposition of two different wave packets, actually the density matrix will display 4 regions where it is non-zero. So that is without bar. These regions on the diagonal you always read off the probability density. They correspond to the left and the right wave packet. And they are just given by psi L squared or psi R squared. But these other spots here in the density matrix, they are like the off-diagonal elements, and they correspond to this interference term, psi L star, psi R, for example. And so they are the ones that depend on an initial relative phase, for example. So I could say this is LL, this is RR, and these are the terms like LR and RL. Now, if I do the same calculation just according to my formulas, but for a state like this, I will see the following. will still see that, of course, there is probability density at the center of mass of the left and of the right wave packet. But the off-diagonal entries will be very much suppressed. Again, depending on the details, but they can be suppressed very much. So they would be very weak or almost not existent. Now it seems like this is a typical case of decoherence, no? Because these off-diagonal terms are suppressed. But if you work it out, it turns out that as soon as the wave packets again approach each other, these extra interference terms become important again, and you do see a nice interference pattern. It will be smeared a very little bit, it will be changed a little bit by the interaction with the environment, but not very much. And so the reason somehow is that in contrast to this which-way information, where you imagine that the electron really has emitted sound waves into the crystal lattice and they will never come back, so there's irreversible loss of information, here the distortion always travels along with the electron. And so there are essentially two Polarons being at two different spots in the crystal lattice. When they are far apart, it seems like there is no interference, no coherence. But as they move closer and closer, again, they overlap and they form a very nice interference pattern. It's just interference of Polarons instead of simple interference of electrons that you observe. And so that's a very important concept. It's very easy to make mistakes at this point. So there's almost perfect coherence in the end when you do measure the interference pattern. And that is because we don't have irreversible loss, irreversible emission of which-way information. If you like, it's a little bit related to this quantum eraser idea, where we began to do a measurement and the state of the spin was entangled with the orbital state of the atom, but then we reversed the setup and undid the entanglement and everything was fine again and we could have the perfect coherent superposition again. So it's a little bit like that. But what is important for this is that the interaction between the electron and the lattice is always there. If I were to suddenly at some point when the wave packets are still separated, switch off this interaction, then I would leave behind this distortion sitting either up there or down there, and then I would have this irreversible emission of which-way information. Okay. And so the real physical effect of such a situation is then only that the electron acquires an effective mass, its properties may change a little bit, the way it reacts to external fields may change a little bit. All of these effects are called renormalization effects. So its properties change, but fundamentally the fact that it remains a coherent particle does not change. Okay. So now we want to get a bit more quantitative. I always said, okay, that depends on the details of the statistical properties of the noise. And so I want to spend at least a little bit of time how you describe this and what are the typical situations that you encounter. So let's start again with the classical noise situation because that's slightly simpler. So think of the spin or think of the wave packets, it doesn't matter. You acquire this random phase phase which can be expressed as an integral over the fluctuating potential. And in the end, you always want to calculate averages of phase factors like e to the minus I phi of t. Now, well, in general, this can become complicated. You would just have to work out what is the probability distribution of phi and then do the integral. And it can have very interesting features depending on the situation. But very often it turns out that phi is a Gaussian random variable. And that comes about because of many different features. For example, it might be that the underlying source of this fluctuating potential is really is ultimately a field whose Hamiltonian is quadratic, and which is in some thermal state or the ground state or anything, and then you will always get Gaussian fluctuations. Or else, even if the source of the fluctuations is not really Gaussian, then if you add up many of these sources, then you can apply the central limit theorem and you still get Gaussian fluctuations. And of course, it helps that the phase itself is still an integral over the fluctuations at different times. So even if these fluctuations during the course of time look very non-Gaussian, you might still be lucky and apply the central limit theorem and phi is still Gaussian. So there are many good reasons why very often it is Gaussian. And so if this is the case, then a very simple formula applies, namely e to the minus I phi average is just e to the minus 1/2 phi squared average. Or phi squared average would be the variance of phi. And here I just assumed, for simplicity, that the average of phi is 0. If this is not the case, I can just shift everything, I will get an extra phase factor. That doesn't really change the story. So what you can see immediately is, in such a Gaussian situation, if the variance of phi is 0, if there are no fluctuations, then this just yields 1. There is no suppression of the interference term, that is what we expect. If the fluctuations are very strong, namely the variance becomes larger than 1 approximately, then the suppression is also very strong. Again, this is to be expected. You average over these many different phases. So this is already a very useful formula. And now you can insert your expression for phi. For example, this integral over the fluctuating energy. And then what you have to calculate is the average over phi squared. Phi itself is this time integral. The square of it will give 2 time integrals and 2 factors, the potential evaluated at 2 different times. So I already pulled the average inside the integral, which I can do. And what we see here appearing in this integral is just the correlator, the correlation function of the fluctuating potential evaluated at 2 different times. So if the noise is Gaussian, then all its properties are determined by the averages, which we set to 0, and the correlators. So it's no wonder that my final result for whatever I'm interested in is also expressed by the correlators. And then in order to discuss the different physical situations, you have to specify the correlator. And sometimes it's the biggest effort is really to look at the physical situation and to model the noise and to work out the correlator. After you know the correlator, everything is simple. Now, of course, there are many different sizes and shapes of the correlator. But the simplest assumption is that if the times are different, then there are no correlations whatsoever between the fluctuations. And only, of course, if the time is the same, then there are correlations. So the kind of noise I'm talking about is called white noise. This is just one example, but a very useful example. And it's very hard to draw it actually, but if you draw it, it would have very wide fluctuations. Actually of infinite magnitude, but that is hard to draw. Okay. And so you can imagine if I take the value here and correlate it with the value somewhere there, and I take the product and the average, they are just as often both positive as one of them is positive and the other is negative, so it averages away to 0. Okay. So the correlator value in this case would be a delta function with some prefactor that determines the strength of the noise. And I want to write the prefactor in a way that is compatible with the more general discussion from later. I want to say, oh, this is the spectrum of my noise evaluated at 0 frequency. But for you, this is just a number here, determining the strength of the noise. Now, if I plug that in, you see the delta function makes one of the time integrals disappear. I just said t2 equals t1. And afterwards, there is no dependence on t1 or t2 anymore. And so I can immediately evaluate the integral and it just gives a factor of t. So phi squared is then 1 over h squared SBV at omega equals 0 times t. Okay. So you see in this case the variance of the phase just increases linearly with time. This is no wonder because in this case actually the phase, which is the integral over this white noise, is a random walk. And the variance of a random walk increases linearly in time. So maybe I can also draw this quickly here. So phase against time will do a random walk. And the distance from the origin goes like square root of t for the random walk, so the variance goes by t. And so if I insert this expression now into my formula for the loss of contrast of the interference pattern, I will just get e to the minus 5 phi average equals e to the minus 1/2 times the variance. Variance goes linear in t, so I get an exponential decay. And so, whenever you have an exponential decay, you can read off a rate, which is the prefactor of the time in the exponent. And so this then would be the dephasing rate, which we usually call gamma phi. Dephasing or decoherence rate. As you can see, it just depends on the strength of the noise, which is reasonable. Okay. Now, this was for a very special case of noise. Of course, I can discuss arbitrarily many examples. And in general, it turns out that instead of just looking at the correlator itself in time space, I should rather Fourier transform into frequency space to get what is called the spectrum. SVB of omega is integral over all times e to the I omega t, v of t, v of 0. That's just the Fourier transform of the spectrum. And you know that without really telling you, I always assume a stationary random process. So the statistical properties don't depend on the point in time. Whether you are here or here, it's just the same. So the correlator only depends on the difference of times. So that's why it's sufficient to Fourier transform with respect to this difference. And so, what would a typical spectrum look like? Well, not a typical spectrum. Like this, for example. It will be symmetric. You can easily show this, that such a classical noise spectrum is symmetric. And it's positive and real. And for example, if you integrate the spectrum of all frequencies, you will recover the variance of the noise, variance of B. Now, if the spectrum looks like this, then there's a typical frequency scale usually over which it falls off. Let me call this 1 over some time. The time I call tau c, because that happens to be the correlation time of the noise. So if I plot the noise in time space, then it does not look any longer as wild as the white noise, but rather it is smooth on some scale, and the scale over which it is smooth, over which the values are correlated, is just the correlation time. Now, of course, the spectrum may look more complicated, may have more structure, then maybe it's not enough to introduce only one correlation time. But this is the basic idea. Now, if I take this situation, and again, I want to work out what happens to the variance of phi in the course of time, I will find, well, in general, a very complicated behavior. It need not grow monotonically, for example. But in the long time limit, that is for times much larger than this correlation time, this noise still looks sort of like white noise. The phase still looks like a random walk on these very long time scales. And so phi squared average will still grow linearly in time. So that's a very generic feature. So for t much larger than tau c, I will have phi squared still growing linearly in time. And interestingly, the prefactor is just the one I already wrote down here. And it's the zero frequency component of the spectrum. So now you see why I wanted to write it in this slightly cumbersome way, because it's just the same expression as before. And just to point it out, what is the zero frequency component of the spectrum? Well, you just put omega equals 0 in this expression. That is, it's just the integral over all times of the correlator. The integral over all times sort of gives you the effective weight of the delta function that you would idealize it with in the case of the white noise. So this is at long times, plus there would be subleading terms that depend on the details. For example, nothing excludes that there's a term going like square root of t or a constant term and so on. But that would be the long time behavior in such a situation with a smooth spectrum. Now, of course, this can fail. For example, if your spectrum at zero frequency is exactly 0, then this leading term is absent, and then you really have to worry about the rest of the terms. Or if the spectrum at zero frequency diverges, then you have an infinite value here, and then you have to look more closely. And it's a different situation again. And so, for example, one other situation that you could come up with rather often is when the correlation time is really infinite. When you have, during the course of the experimental run, the noise just staying constant, and then only being a different value for each run. In that case, you would have a growth like t squared. And so the loss of coherence, instead of going exponentially with time, would go like a Gaussian, e e to the minus t squared. And so that's a typical case if the noise is very, very slow on the scale of the experimental time scale. It also occurs if you just have an ensemble of many different systems, for example, many spins in a crystal lattice. Each of them sees a slightly different magnetic field, for example. And so that corresponds to different values of B, effectively, and you average over them. And you look at the average oscillations of, say, the x component of the magnetization, and you would then immediately, again, find such a Gaussian decay e to the minus t squared. And so that would be called inhomogeneous dephasing. So there are different cases, but this is a very generic case. Or I might add that, again, if you have such a smooth spectrum, if you go to the short time limit, then the behavior at which it starts is just t squared. Instead of t, it's t squared at short times. So, for example, if you are interested in qubit physics, you can amuse yourself by working out the spectra and what it means for the coherence of your qubit. And then you can go further. This is something which we don't have time to discuss. Then in spin physics, you can do so-called echo pulses and get rid of the low frequency part of the noise, but you will still feel the high frequency part of the noise. And so again, this is quite interesting. Okay. So much for the classical description of the noise properties. And the next thing I want to discuss is the quantum mechanical version. Okay. So if I want to describe the quantum version, I have to write down a Hamiltonian. And again, let's just pick the simplest possible case. So to speak, it's an exercise for the audience to look at the more complicated cases. But this already shows all the principles. So let the Hamiltonian be one part, going back to the spin case, one part that describes the free evolution of the spin, just some transition frequency and nothing else, plus a part that describes the interaction, plus a part that describes the dynamics of the bar. And now I want to make it relatively simple. I want to say, well, my interaction is just of this type. If the spin is in the up state, then its energy fluctuates according to some operator, in this case, that depends on the bar. So this is the quantum version of what we had previously, where we said, oh, the energy of the upper state just fluctuates in the course of time as some prescribed random noise potential, whereas here V is really an operator that acts on the bar. And of course, if you are able, for example, to prepare such a situation where can be approximately treated like a classical variable because, for example, it corresponds to the amplitude of a very highly excited state, then again go back to the classical situation. Okay, so initially I assume the state is just this equal superposition of up and down. I don't even write the 1 over square root of 2 here anymore. And the bath, of course, I also have to specify the state of the bath. The bath may be prepared in the ground state, as is a usual situation at low temperatures, or in some arbitrary eigenstate, for example, or even in some completely arbitrary state. Anyway, I will call this initial state chi naught. Now, what happens with this state in the course of time? Well, as we discussed several times, the initial bath state will evolve differently depending on whether the spin is up or down. If the spin is down, then it will just evolve according to the unperturbed bath Hamiltonian. If the spin is up, it will evolve according to the bath Hamiltonian plus this extra operator B. So the state will look like this. Down, entangled with some time evolution operator which I call U down of T acting on the initial bath state, plus the same for up and a time evolution operator U up. And so U up or down of T, well, that's just time evolution operator acting purely on the states of the bath, but being different for these two cases. So I call it e to the minus I over h bar, h up or down, times T. This is a time-independent Hamiltonian, so it's relatively simple. But what is h down? This is just the bare bar Hamiltonian. And h up is just the bath Hamiltonian plus v. Because if I'm in the up state, then this projector onto the up spin can just be replaced by its eigenvalue 1. And so then I have this plus v. Okay, so I simplified the situation a little bit in the sense that I didn't put in a v up and a v down, which would have been still slightly different. But it's not so complicated to treat that. Okay. Now, this, so to speak, is chi down. That will be chi up. In the end, we have to calculate the overlap. So, chi down of T, chi up of T would be, if I insert these terms, then chi up is obtained by having this time evolution operator U up. And chi down, I would have U down acting on chi 0. This is in the bra part of the scalar product. So if I rewrite it, I will put this time evolution operator here by having the adjunct. So it's U down dagger of T. And so I want to calculate the expectation value of this product of evolution operators with respect to the initial bath state. And this is really the kind of expression that always occurs in this setting, even if I had a slightly more complicated version here. Chi 0 can be arbitrary. I could also have thermal average, which just would mean an additional average out here. Now, the way to write this in a suggestive format that is very close to the classical version is to express this time evolution operator, which has this extra v in here, in the interaction picture with respect to the bare-Barth Hamiltonian. Because usually, or hopefully in most of the cases, the bare-Barth Hamiltonian is relatively simple. It might be the free electromagnetic field, where you just have all the normal modes, each of them is a harmonic oscillator. It might be the free sound waves in the crystal lattice, so it's very often a free Hamiltonian, or at least it might be free electrons moving inside a matter. So it makes sense to go into the interaction picture with respect to the Barth Hamiltonian and to write down everything in terms of that. And so then the result happens to be the following. It's the average, that means expectation value with respect to Chi0 of the following expression. It looks very similar to the classical case. E to the minus I over h bar, integral over time, v of t prime dt prime, where v of t prime is now the interaction picture of the Heisenberg evolution with respect to h bar of v. And since this is an operator up there in the integral, and these operators taken at different times usually will not commute, it can't be that simple. You still have to have a time ordering symbol here. So again, what do the different symbols really mean? This is the time ordering. So it's not an operator, yeah. It's just something that you can, whose action you can work out only as long as you keep this integral formally and then develop it down into a Taylor series so that you get products of many v's. And then the idea is that whenever you encounter such a product of many v's taken at different times, you should just push the smallest time to the right and order it in this fashion without introducing any signs or so, just order it. So it's not really an operator, it's just a formal prescription of what to do with this expression if you expand it in a Taylor series. So it takes the smallest time to the right. In products of V. So for example, it would be very, very wrong to first calculate this time integral, which you might want to do if this is just a 2x2 matrix, for example. And then afterwards, you worry, how should I apply the time ordering symbol? Okay. Now, V of t prime, as I said, is just the Heisenberg picture evolution of V with respect to the Barth Hamiltonian. So that is e to the plus I over h bar times t e to the minus I over h bar times t. Okay. Now still it's a very useful formula because it's easy to remember and very close to the classical version. And it becomes even nicer because it turns out that in many cases, as I said, the Barth Hamiltonian is just a quadratic Hamiltonian describing some free bosons. If then this is the case, and the initial state is also a simple state, like the ground state of harmonic oscillators, or some thermal state of harmonic oscillators, or in general any Gaussian state with Gaussian Wigner density, plus V itself is linear in the coordinates of these normal modes, in the coordinates of the harmonic oscillators, then I can simplify this expression in a way which is again very reminiscent to the classical case. So, if HB is quadratic and Chi0 is Gaussian and V then all this average can be simply evaluated. And it is e to the minus, as you might expect, it just looks like the classical case. So as if you say e to the minus 1/2 the variance of this. And the variance is just the square and taking the average. And there's only one little detail here. Of course, since these are operators, again, the order will matter. And all you have to do, it turns out, is to pull the time ordering symbol inside the correlator. Okay. So the dt1 and dt2 are part of the integral and the exponent, of course. Now, since they don't commute, in general, this integration will also give imaginary contributions. And these imaginary contributions in the exponent for this overlap will then give rise to things such as effective energy shifts, because it's like e to the minus I omega t with some effective omega. Okay. In any case, what we learn from this simple calculation is, again, the correlator appears. Again, we should ask about the correlator. By the way, if you are interested in what happens if I really would have two different V's for the two different up and down spins, the calculation would be similar, only then also U down would be non-trivial. So here I would have something that takes V up and orders the times with the smallest time to the right, but in front of this I would have yet another such time evolution operator where I have e to the plus I over h bar because it's the adjunct, and I order the times in different direction. And instead of V up, I have V down. And so you can write an expression that is completely identical looking, only that, so to speak, the time integral runs from 0 to t and back again. So you have two parts of the trajectory called the forward and backward part of this time path. And then there would be a time ordering symbol, which is called a Keldysh time ordering symbol. So if you want to know more about that, look for the Keldysh time ordering. But that gets a bit technical, so I didn't want to do this. Now what we want to discuss rather is the correlators, the quantum correlators. And again, it's best to look at the spectrum, to look at the Fourier transform. So when we take the Fourier transform, we really take the Fourier transform of the correlator itself. We don't do the time order correlator because there would be different versions of time ordering. Once I do the Fourier transform of the correlator, you can always go back by the backwards Fourier transform to time space, and then if you like, you can time ordering anything you want. So what we have here is again a noise spectrum, but it's now a quantum noise spectrum. And it's a really very useful concept in all of this field. So it's nothing but the Fourier transform of the correlator. And I just draw a typical noise spectrum of this kind. Again, it's real valued, it's non-negative, but in contrast to the classical noise spectrum, it need not be symmetric in frequency. So, for example, it could look like this. So SVB is non-negative, but not necessarily symmetric. And we will see in a moment that this asymmetry has important physical information. Now, in order to appreciate what this means, we want now to go to a situation which is slightly different from what we discussed before. We always had this QND type of interaction where the noise would just basically have the energy difference between up and down fluctuate. But of course, this is not the only situation. Think of an atom that is coupled to the electromagnetic field. The simplest process that can happen is that if the atom is in the excited state, it just emits a photon. It emits energy into the electromagnetic field. And so this is just a result of having an interaction part in the Hamiltonian that is different from what we had before. It's no longer of this QND type, rather it lets the state of your atom flip from excited to ground state. So, in general, that means we are now interested in relaxation processes, and the spectrum here will give us the relaxation rates. So again, I have to specify my Hamiltonian. Let's say the frequency difference between the states again is omega. Plus there is the interaction, plus there is the Bath Hamiltonian. And the interaction I will now take like something that can actually change the state of my spin or my atom. And so the simplest version would be to take sigma x. It flips up to down and down to up. And I couple it to some operator of the Bath. Again, let's call it B. And note that I did not introduce any asymmetry here. Sigma x flips up to down, but also down to up. All the asymmetry in relaxation versus excitation comes only because it's usually more likely to find the Bath in a low energy state than in a high energy state. Okay, so that would be H end. And the situation is like this. We have up and down. There's a frequency omega, transition frequency. And what can happen if I place it in the upper state? It can just relax to the ground state and emit some quantum of energy into my Bath, if I think of photons or phonons. Or in general, it can just emit energy to the Bath. Okay. Now the task we want to set ourselves is just to calculate the rate at which this happens. So we have in mind a situation where the coupling strength here is effectively very small. I could introduce an extra epsilon here and then formally let epsilon go to 0, but it doesn't matter. Maybe the V already contains the epsilon. Yeah? So I will imagine that the coupling strength is very weak. And then it turns out perturbation theory is a very good approach. And I can use Fermi's golden rule to calculate the transition rate. And you know, Fermi's golden rule requires as input, well, basically three things. What is the initial state, what is the final state, and what is the perturbation that acts. Yeah. For us, of course, the perturbation is just this interaction part of the Hamiltonian. The initial state, well, should probably be that the spin is in the excited state, and the Bath is in some initial state, chi 0. And the final state will be the spin in the down state, and the bath in some final state. There will be many final states there that are compatible with this transition, and we will have to sum over them. Okay, so Fermi's golden rule. Which was not invented by Fermi but popularized by him in a book, has the following initial state: up times chi 0, and the final state I take to be down times sum. Final state, and I will take this to be an energy eigenstate of the bath, just arbitrarily, generally speaking, and we will sum over that. Okay. Now, one important concept here is the following. I'm really only interested in the rate of up going to down. I'm not really interested in the detailed state in which the bath ends up. So that is why I will sum over a bunch of relaxation rates. So the gamma for the process of up going to down is really a sum over over all final bath states I have of the more detailed transition rate for the transition from I to F. Yeah. So this is very important. Now, what is gamma from I to F? Well, I just apply the usual formula. So that would be 2 pi over h bar. And then you need the matrix element of the perturbation, that is the interaction in our case, between initial and final state. And you square that. Plus, there's another important ingredient, which is this energy conserving delta function, which tells you the total energy of the initial state must equal the total energy of the final state, unless I were to have some time-dependent perturbation, which I don't have. Now, these energies, let's look at these energies. The energies are to be calculated without taking into account the perturbation. So only this part of the Hamiltonian and the bath part of the Hamiltonian. And because of that, they are just the sum of the spin energy and the bath energy. So, for example, EF would be the energy of the down state, because finally we are in the down state. This happens to be 0, but I want to write it down here for clarity. Plus the energy of the bath in the final state of the bath. So that would be the energy of chi F. And the same for the initial state. And now, the point is that we can simplify things because we are doing the sum over the final bath state. I will not go through the details here. It's a nice little homework problem. The trick is to express this delta function as an integral over time of e to the I omega t, and then to rearrange things and make use of the fact that the sum over all final bath states is like a sum over projectors of these bath states in the end, and so it's just unity. And so if you do all of that, you can write down a very, very nice, simple formula, and this is really important, really useful. So the rate for going from up to down can be expressed in this way. It's just 1 over h bar squared times the spectrum, the quantum spectrum, evaluated now not any longer at 0 frequency. That was important for the dephasing that we discussed. But the frequency at which you should evaluate the spectrum now is just the transition frequency between up and down. So in our case it's omega. But I will write it down in a slightly more general way. It's the difference in energies between up and down. So So you see that all these details of the matrix elements and so on, all these delta functions, they have vanished. Everything is expressed in terms of the spectrum, and the spectrum is just the Fourier transform of the correlator. So everything becomes very, very simple. Yeah? Once you tell me what is the correlator, everything else follows. So this is important because both technically it's simple in the end, and also conceptually it's nice because it shows you, give me the spectrum and I tell you everything. And that's a consequence of having this weak coupling situation. Yeah? If you had stronger coupling, then instead of just having to look at the correlator of B, you might have to look at higher order correlation functions, because up to now, we didn't even specify what is my bath spectrum. I don't claim this should be quadratic or that the initial state should be Gaussian or anything like that. These are completely general formulas as long as the coupling is weak. Okay. And so likewise, I can also calculate the rate for transitions in the other direction. If I go from down to up, yeah? And it happens, this is also very simple. It's just the same expression, only that here, of course, initial and final state are interchanged. So you evaluate it effectively at negative frequency. Okay. And so, regardless of the situation you face, if you are sure that you have this weak coupling case, the real task lies in calculating the spectrum. Well, first writing down the Hamiltonian, so you know how to identify V, and then to calculate the spectrum. And so I think next time we will just discuss a little bit further the spectrum, but what you see already is now that these formulas give you a direct physical meaning, because some of the downward transition rate will be related to the spectrum for positive frequencies, and the upward transition rate will be related to the spectrum at negative frequencies. So if you couple your bath, whatever it is, to such a two-level system weakly, and you just observe the transition rates up and down, you immediately can tell what are the values of the spectrum at